Welcome back, my degenerate eigenfollowers. Today we're going to be doing something a little bit different compared to the quantum series that I've been working on. We are going to be going over what's known as the coupled harmonic oscillator. And this particular problem incorporates a lot of really useful physics and mathematical concepts that can extend to a whole array of different physical phenomena. Okay, so what we're going to be doing is determining what the frequencies of oscillation are for this system and the normal modes. And the frequencies of those oscillations correspond with the eigenvalues, and the normal modes correspond to the eigenvectors. But before we even can solve that and determine what those are, we need to put together the equations of motion describing the system. And there's two different ways that you can go about determining those equations of motion. There's probably more than two, but the ones that I'm going to incorporate here are going to be the old-fashioned Newtonian way, where we incorporate Hooke's law and whatnot. And then we're also going to use the Euler Lagrange equation to construct our differential equations. So both are valid, and I think it's very useful to incorporate two just to kind of check your answers to make sure you're getting like the correct result. So it's a nice sort of like contingency plan, right? So let's get started here. So what do we need first to describe the system? Well, we need Newton's second law, right? So let's write that out. We have N2, and this states that the force is equal to the mass times the acceleration. But we're going to be using the dot formalism to describe our differentials, right? So x double dot is just the acceleration. A single dot would be the velocity. So we're gonna stick with that because it keeps everything internally consistent when you're working with, this part here that describes the origin points of our masses. So just sort of makes it a lot more internally consistent. So next, what else do we need? We need Hooke's law, right? So Hooke's law says, so we got Hooke here. So Hooke's law states that the force, when you're dealing with a spring, is equal to minus kx. K being our spring constant, and x just corresponding to the displacement. And it's negative because as you exert a force in one direction, that spring exerts an equal and opposite force in the opposite direction, trying to bring itself back to equilibrium. Okay, so these are going to be the equations that we're going to be using for some time now. So let's start. So let's look at our first mass here, right? So our first mass, if we're looking at a displacement to the right, well, as I've mentioned before, it's going to exert an opposite force to the left to restore itself to equilibrium, okay? So if we're starting out with our force here, we're going to use Newton's second law, so mx double dot, but this is x sub 1. And this is going to be equal to, this is going to be equal to the force that is exerted in the opposite direction. And because our spring constant on this part of the spring is 2k, that is what we're going to be using. So we're going to use negative 2k x1 for our first one. Now let's move over a little bit and look at this spring relative to this mass here. Well, if we're exerting a displacement to the right here, that spring is going to compress, but it's going to exert an opposite force to, once again, resist that compression. But this time we are keeping in mind that this mass here is also contributing to that sort of restorative force here. So we have to be sure to include that in our equation here. So as before, we're going to introduce a minus sign to indicate that it is acting in the opposite direction. And because we're concerned with the largest force in this particular part of the spring, we're going to be using 2k, right? And then we are going to be subtracting off the contribution of this part here. So it's going to be x1 minus x2. Okay? So that's our first equation here, or our first differential equation, essentially. So this is going to be equal to, well, let's just expand this out. When I distribute that, that is going to have a like term corresponding with this term. So this will give us negative 4k x1 plus 2k x2. So this is our first equation that we're going to be using for this part of the spring. Now let's bring our attention over to this mass here. So as before, we're going to be invoking Newton's second law. To describe that force is going to be m, actually not just m, because this mass happens to be 2m. So we're going to put that right here. So 2m, and then that's going to be x double dot 2. Okay? So as before, we are going to look at this part of the spring now. And as we are exerting a displacement to the right, it is going to correspondingly exert an opposite force, because instead of compressing now, you're sort of extending this part of the spring by applying a force in this direction. So that spring is going to act to the left, right? So as before, we're going to have a negative, and because we're concerned with the largest force in this particular part of the spring, we're going to subtract off x sub 1 in that. So this is going to be minus 2k, and then x sub 2 minus x sub 1. Great. All right, so now let's look at this part of the spring. And now we're introducing a compression to this spring here. And as before, it's going to exert an opposite force in the opposite direction. And we are going to have a minus. And because we have 4k as our spring constant there, this is just going to be minus 4k x sub 2. All right, now expanding this out, we're going to have like terms again, which is going to give us minus 6kx2, but I want to keep this sort of sequential. So our first term is going to be 2k x sub 1, and then minus 6k x sub 2. Great, so there we go. We have our set of equations. So now I want to introduce the Lagrangian, so we can sort of check these answers to see if we're correct or not. So the Lagrangian is essentially just the difference between the kinetic energy and the potential energy of our system. So that looks like, so we have our Lagrangian, which is equal to T minus V. So kinetic minus our potential. And then we also have our Euler-Lagrange equation, which is simply just the partial derivative of our Lagrangian divided, or our partial derivative with respect to our function q. So it's going to be dq, right? And that's, we're going to subtract off our time derivative, so a total derivative this time. So d dt, and that is going to be differentiating the partial derivative of our Lagrangian with respect to q, but it's going to be q dot. And maybe one day I'll derive this for you guys, but I just hope you'll take my word for it for now. So this is going to be equal to 0. All right, so we have what we need here to start constructing our equation using this particular method. So first we need to figure out what our kinetic energy is. And before I even do that, I want to write out a free body diagram to get a closer look here, so we can kind of see everything going on. All right, so we're going to have our first mass, which is m, and recall that force that is going to be acting opposite to the displacement is just going to be this right here. So this corresponds to 2k x1. And because we are still considering that force displacement to the right here, this is just going to be mx double dot sub 1. Okay? Now, as we look at this part of the spring, recall it's just going to act in the opposite direction as we compress that spring there. So we're just going to get 2k x1 minus x2. Cool. All right, so now we have everything we need. We can start constructing our Lagrangian. So what do we need? We need our kinetic energy. So T, well, that is going to be, you guessed it, 1/2 mv squared. So 1/2 mv squared, but instead of v, I'm just going to do x dot squared. And because we're dealing with x sub 1, that is going to be the one we're concerned with at the moment. So there we go. We have our kinetic energy. Easy peasy. But our potential, well, our potential just corresponds to the sum total of all those forces that are acting opposite to the displacement here, okay? So what is the potential we need for this particular kind of a problem? Well, because we are dealing with a harmonic oscillator, we're going to have to use the harmonic potential, which is just 1/2 kx squared, right? So 1/2 kx squared, right? So that is what we're going to be using to relate these forces here. So if we write all that out, well, that 2 is going to vanish because of this 1/2 here. So we're just going to get kx1 squared, right? And then we're adding that to this part of this force right here. So that 2 is going to vanish again, so we're just going to get kx1 minus x2. Perfect. And that's going to be squared. Don't forget that. That is important. So let's extend this out, and we're going to get kx1 squared plus, all right, so let's do our outer terms first. So we're going to have kx1 squared, so kx1 squared, and then let's do our outer terms, which is going to be plus, and that's going to be plus kx2 squared, and then we're going to subtract off our cross terms here, so minus 2k x1 x2, and we can simplify this a little bit. We're just going to have 2k x1 squared plus kx2 squared minus 2k x1 x2. All right, now we have everything we need to start using the Euler-Lagrange equation we have here. So let's differentiate our Lagrangian after putting it together, of course. So basically we have to take this, subtract all of this off. So our Lagrangian, I'm getting a little ahead of myself here. So this is going to be equal to 1/2 mx dot 1 squared minus 2kx1, 2kx1 squared minus kx2 squared plus, I'm running out of room here, plus 2kx1 x2. I hope you can see that. So there we go. So now we can differentiate here. So if we differentiate our Lagrangian with respect to x1, well, we can treat everything else that isn't x1 as a constant. So what we're going to end up with is this equal to minus, so that's going to be minus 4 kx1. Okay, that vanishes because everything's a constant there. All constants there, and this is just going to be plus 2k x2. All right, so we have our first one. So now let's differentiate with respect to q dot, or x dot, x1 dot. So what do we get here? So we're going to get this with respect to x1 dot. And as before, we can treat everything else as constants except for x1. That is going to, just good old-fashioned power rule, is just going to be equal to mx1 dot, okay? Because that removes the 1/2 term there. Okay, so all we need to do now is differentiate this term with respect to time. So if we do that, we're going to have, let's see, try that again. So we're going to have d dt of the differential of our Lagrangian with respect to x dot 1. And all that really is just mx1 double dot. So Newton's second law. So mx double dot sub 1. All right, so at this point, all we really need to do is put everything back together. So if we subtract off this, well, this term is just going to be mx1 double dot. I'm going to take that and add it over to the other side. So what we end up with is mx double dot sub 1 is equal to minus 4k x sub 1 plus 2k x2. And there we go. Now, does this look how it's supposed to look? Well, as you probably have already noticed at this point, these equations are identical. So now we can do the same thing, play the same game for x sub 2. So I'm going to clear off some of the space and we're going to go through and figure out what x2 is using this particular method. All right, so I took the liberty of writing out this free body diagram here, and we can see here it's very similar to the previous one, but on this side here we have the force that's acting opposite to the spring acting opposite to the displacement at this spring, which is 2k x2 minus x1, and then as before, our displacement here just corresponds to the applied force in the right direction, which is mx double dot sub 2, and then the force acting opposite in this direction on this part of the spring is just 4k x2. So all we need to do is just use the same sort of tools here that we have. So we're going to have T, which is our kinetic energy. We have 1/2 mx dot squared sub 2. So that is our first term here. All right, so we just want to add up our potentials now. So our potential is going to be this first term here, which is 2k x2 minus x1 squared, and plus this term here. Well, as you probably have already noticed, that 2 just vanishes when we introduce that 1/2. And then that 4 just becomes a 2, so there's just going to be 2k x2 squared. All right, so let's extend this out here. So this is going to be kx2 squared for our outer terms. I'm going to add that together with this term. So we're going to get, so kx2 squared plus 2kx2 squared, which is 3kx2 squared. And then we're going to have plus, so kx1 squared plus kx1 squared. And then our cross terms, which is going to be 2k x1 x2. All right, so now we can start putting together our Lagrangian. So let's do that. So our Lagrangian is just the kinetic minus the potential. So we're going to have 1/2 mx dot squared sub 2 minus 3kx2 squared minus kx1 squared plus, I'm running out of room again, 2kx1 x2. All right, cool. Now all we need to do is just apply our partial derivatives here with respect to x2 for the first one. So this is going to be the derivative of our Lagrangian with respect to x sub 2. As before, we can treat everything as constants. This is going to be negative 6k x2, so negative 6k x2. That vanishes, and then we have plus 2k x2, or x1, excuse me, 2k x1. All right, cool. Now we need to just apply this. So we're going to have d Lagrangian with respect to x2 dot, which is going to give us m. So this all basically vanishes. So this is just going to be mx dot sub 2. And if we apply the time derivative, we get the derivative of our Lagrangian, x dot 2 is, as before, just mx double dot. So mx double dot. All right, and I'm sure you can already see where this is going, but let's just, for completion here, let's see it through. So we're gonna take this term, subtract off that term. I'm gonna move this over to the other side, and we're just gonna get mx double dot sub 2 is equal to 2k x1 minus 6k x2. All right, there we go. And as you can see here, this is exactly what we put together earlier. So this checks out, and now all we really need to do is take these equations and figure out what our frequencies of oscillation are. So I'm gonna clear some of this up, and we're gonna start going through it. All right, so to find the frequencies of oscillation, we have to find the eigenvalues. And the best way to do that is to put this into a matrix form, okay? So let's basically take all this and put it into a matrix. So for our left side of the equation, we're gonna have, well, actually, before I even do that, I think it's best to make sure our masses are consistent. So I'm gonna multiply both sides, if this, by 2, right? So we can sort of factor out an equal amount of mass from our column vector that we're going to be making. So to put this together, we're going to have 2m. So I'm factoring this out here, and we're going to have x double dot sub 1, x double dot sub 2. Cool. All right, now that is going to be equal to this side. We're going to be using these k constants, and what I'm going to do is I'm going to factor out our k terms here from our matrix. So remember, I'm multiplying this by 2. So I'm also going to factor out a minus sign, and you'll see why I do that later. So I'm going to factor this out. So we're going to get minus k, and our matrix is going to look like, so we're going to have plus 8, so 8, and then we're going to have minus 4, and down here we're going to have just 2, or rather minus 2, and then plus 6. I don't know why I wrote that. All right, so plus 6. Now, and this is all going to be multiplied by x1, x2. All right, so we just about have our eigenvalue problem. Now, what we need to do now is construct what's called an ansatz. And an ansatz is just it's German for like an educated guess, basically. But we can sort of infer what this partial derivative is going to be if we invoke a harmonic sort of trig function, basically, right? So if we were to do that, say we have x1 is equal to, so that's equal to some amplitude times cosine of omega t, which is just the angular frequency, times t plus some phase. Okay, so that's going to be plus some phase that we're using with. Now, if we're going to differentiate this twice, right? Well, that is just going to give us, if we differentiate this twice, we're going to get minus omega squared. So minus omega squared times a. And this brings us right back to cosine, because you differentiate this once, you get negative sine, then negative cosine. So this is going to be cosine of omega t plus our phase. So this is going to be our ansatz. We can basically absorb this into our x's here. And basically what we can do now is write out what this must be. So x1 double dot, x2 double dot is going to be equal to minus omega squared times just x1, x2. Right? So there you go. This is what we're going to be effectively substituting in for our differentials here. So let's do that. So what I'm going to have now, after I substitute this in here, we're going to have minus 2m omega squared times, now we just have x1, x2. All right, and that is going to be equal to, as before, just minus k, 8, negative 4, negative 2, and 6, which gives us x1, x2 for our column vector. All right, so now I'm going to just rearrange this a little bit. I'm going to divide out this 2 to this side. So I'm going to divide each of those elements by 2. And then I'm going to divide this negative k. Now you see why I have that negative sign there. So it'll become positive, right? So now we're going to have m omega squared over k. Okay? And we're going to have x1, x2, that's going to be equal to, so divide out by 2, we're going to get 4. So 4, we're going to get negative 2, negative 1, and 3. So there we go. So x1, x2. All right, so at this point, we have what's called the Eigenvalue Problem. And this right here is just our eigenvalue, right? So this is just lambda. So lambda is equal to m omega squared over k. Cool. And that, as you could probably guess, this is just our frequencies of oscillation that we're trying to find. So we can make some substitutions. That's just going to be lambda. And the eigenvalue problem states that if you take the determinant of some matrix, the eigenvalues will be some matrix minus your eigenvalues times some identity is equal to 0. So you have this non-trivial null space you're working with. All right, so let's write this out now. So you can see here, I'm basically just going to be subtracting from this side, bringing out our identity matrix, and we're just going to get, let me clear this up a little bit. So I'm going to move this out of the way. And what we're going to get, so we're going to have, so basically when I subtract this out, we're going to have the determinant. We're going to have 4 minus lambda, and then negative 2, and then negative 1, and 3 minus lambda, and that is going to be equal to 0. Okay, so now we can just take this determinant, multiply this diagonal, subtract off this diagonal, and that is going to give us, we're going to have 4 minus lambda times 3 minus lambda, and then these become positive, so minus 2 equals 0. All right, so now we can start putting this all together. So 4 times 3 is 12, minus 4 lambda, minus 3 lambda, so that's going to be minus 7 lambda, plus lambda squared minus 2, and that equals 0. So at minus 2, we can rearrange this a bit. We're going to have lambda squared minus 7 lambda plus 10 is equal to 0. All right, cool. So now all we really need to do is factor this. You can always use the quadratic equation if that suits you, but I'm just gonna do it explicitly. So we're gonna have lambda something, right, and lambda something. Well, if we want to add up to equal -7, we're gonna have to subtract both sides by 5 and 2. 5 times 2, -5 times -2 is 10. -5 plus -2 is going to be -7. 7 lambda. So that gives us our frequency modes, right? So we're going to have a lambda is equal to 5 and lambda is equal to 2. There we go. We have our frequencies of oscillation. So these values correspond to this right here. And now all we really need to do is find the eigenvectors that correspond to our normal modes, which are essentially just the modes at which a sinusoidal wave sort of oscillates in phase relative to these particular frequencies of oscillation. So now all we really need to do is sort of plug these back in and solve for our eigenvectors. So I'm going to clear this off a little bit, and we're going to solve and figure out what our eigenvectors are. All right, so now we're going to find our eigenvectors. We have our matrix that we're going to be using and what our eigenvalues are. So to find what our eigenvectors are, for each particular eigenvalue, we're going to take our matrix and subtract, that's an equals, we're going to subtract our eigenvalues off of it, where our eigenvalues are multiplied by the identity matrix, and we're going to multiply that by some column vector with x components associated with it. And that is going to be equal to 0. So we're solving for this here, right? So all we really need to do is subtract off lambda. All right, so for lambda equals 5, let's do that one. For lambda is equal to 5. All right, so let's start working this out. So we're going to get 4 minus 5, which is -1, -2, -1, 3 minus 5 is -2. And this is all going to be multiplied by our column matrix, x1, x2, and that is going to be equal to 0. Okay, so before we do anything here, it's good to have a little bit of an internal consistency check. So to ensure that you have set this up right, you're on the right track, it's best to row reduce these. And what you should end up with is a row of all zeros. There should be essentially a row that is linearly dependent upon the other components here. And that's exactly what you want to see. So if we do row 1, so let's multiply row 1 by -1 and add that to row 2. And that's going to give us, we're going to have -1, -2, multiply this by -1, this row becomes 0. And there we go. That's exactly what we're looking for. So we are on the right track. So we're going to multiply that by our column vector, x1, x2, set that equal to 0, and just start multiplying this out. So what we're going to get now is -x1 minus 2x2 equals 0. And we can move that over. We're going to have -x1 equals 2x2. And at this point, you can really select any x value you want, but it's best to just keep it fairly simple. So we can select, let's say, let x2 be equal to 1, right? So let's let x2 equal 1. All right. So what we're going to get is just -x1 equals 2. And we can divide out that negative sign. So that is just going to be x1 equals 2. All right. So that is going to be, this is going to be -2. So there you go, that's our eigenvector. So our first eigenvector we're going to have, so we'll just call call it E sub 1, is going to be equal to, we're going to have -2 and 1. And what you can do to maybe have another little bit of a checkpoint here to determine whether this is right or not, you can multiply this by your original matrix. And whatever you get should provide you with the same vector scaled by by the same eigenvalue you used to find it. So to check it, let's say we have 4, -2, -1, and 3. Well, let's multiply this by our eigenvector. See what we get. So -2, 1. And if we want to multiply this out, what we're going to get, so our first row poured into this column is going to be 4 times -2, which is -8. And this is going to be plus -2 or -2. And then our first term, we're going to get -1 times -2, which is 2 times, or plus, times 3, so plus 3. And let's see what we get. So if we add these all up, we're going to get -10 and 5. Well, this doesn't really look like our eigenvector, but if we factor out a 5, we get exactly what our eigenvalue is. So we're going to have 5, -2, and 1. There we go. That is our eigenvector. Perfect. So all we really need to do now is apply the same rule and find our next eigenvector, and we will be done. All right, so let's try eigenvalue 2 now. So we're going to have lambda is equal to 2, and we're just applying the same rule here. So 4 minus 2, that's going to be 2, -2, -1, 3 minus 2 is 1, and now we basically just need to determine what x1, x2 is. And that's going to be equal to 0. All right, so let's do a little bit of a row reduction. So let's multiply this row. So 2, let's multiply this row by 2. So we're going to get R2 times, that's R1. So 2 times R2 is going to give us -2, and then we're going to add that to row 1. All right, so multiply this times -1, add it to this, we get 0. Multiply this by 2, add it to this, we get 0. Cool. We got exactly what we want. And x1, x2. All right, cool. And now we can just do our good old-fashioned multiplication. So we're going to have -x1 plus x2 equals 0. And then we'll add this to the other side, so x2 is equal to x1. And we can just let both of them equal 1, right? So this is going to give us our eigenvector 2 just equal to 1, 1. And there we go. We have our normal modes. Just for safety's sake, just to check to see if we did this correctly. Let's do 4 times -4, -2, -1, 3, and then we're gonna have 1, 1. Let's multiply this across. So we're gonna have 4 minus 2, and then -1 plus 3. All right, and this is going to give us, we're going to have 2 and 2. And lo and behold, we have our eigenvector scaled by our eigenvalue of 2, which we see is just 2, 1, 1. And there we go. These are our eigenvalues, which correspond to the normal modes of oscillation. So we're going to have 2, not 2, so 1, 1, and there we have it. All right, so I know this was probably just a little bit painful, or at least just long-winded, but I think it's just a very, very important problem that introduces a lot of very, very important physics and math. And I really hope you enjoyed it. I think this is a really fun problem. There's, I mean, just a lot of different applications that this can relate to, you know, even in quantum mechanics. So, I mean, it's a very ubiquitous problem, or at least the concepts involved are very ubiquitous. So, that being said, I hope you stay tuned. I have another video in my quantum series coming out very shortly. So, keep an eye out for that, and see you later, calculator.